So good afternoon, everyone. If someone that requires a certificate hasn't signed the list for today, please do so. There are few of the posters for tonight's session that are not there. So if it's your case, please go and put your poster there. Okay? And it's my pleasure now to introduce José Dias do Nascimento Jr. He is from Federal do Rio Grande do Norte and is spending a lot of time at Smithsonian at Harvard University recently, and have been working from a long time in the stellar rotation and using velocity measurements of stars. Thank you for coming.
Thank you, Eduardo. Thank you, everyone. I try to keep you wake up. It's not easy at this time. So yeah, in fact, I try to show some results from my team, from my collaborators, my students. Of course, I'm not the major of all these results, but I compiled something from these nice people from CFA, some guys from France. And yeah, well, that is Natal, just to keep you, this is my home city. I spent some time there, some time in Cambridge, but in general, I'm in this environment. So Natal has this group of astrophysics. It's a small group. This is my team. This is a new professor. He's a French. Nobody's perfect, but yeah. Another, this is my first student. This is Professor 2, just to mention to you guys. So I'm thirsty in activity because activity has these nice things to do with exoplanets now. And of course, activity of the stars is a major problem to the space weather physics. So I spent a lot of time with spectropolarimetry measurements. And this is a kind of nice tool, but today, I'm sorry for that, I'll not talk about spectropolarimetry, but I talk about magnetic field. The reason is easy. This is a paper of a planet. This is a nice paper, published in 2 papers from Cape Tinin star. So these 2 super-Earth planets was published in 2014. The nice thing also is that 1 year after, another group say, no, this is not a planet. In fact, this is an artifact of stellar activity. And 1 year after, no, this is a planet. In fact, we have 2 super-Earth candidates in this star. So this confusion about planet or non-planet, or this fake planet, comes from this rotation period. In fact, depending on the rotational period, we can put the planet in or out of the data. So the problem that we're facing is this kind of problem. So we have active star. It's not the really active star, but it's the sun. And the kind of planet that we search for, it's like this. So this is a well-known problem. And because the sun can put a lot of noise in the data from exoplanet search. My outline of the paper, I try to show you the rotation ideas of the state of the Earth of rotation, the activity cycle of the stars. I push for stellar activity. I mean, I discuss a little bit about this planet in habitable zones, and finally, I draw my conclusion. So, radial velocity measurements is a kind of very, very nice thing that's coming in the last year and continue the next year. Here, a lot of instruments are proposed. Of course, the G-clef is here. I would like to underline, I mean, Espiro has some Brazilian time there, and we have NIRPS is the only instrument in the infrared in the south. So we have a lot of fun in the next year in radial velocity. So just for students, we need to remind that planet mass are computed from spectra, and spectra are affected by activity. So one of the problems in determining fundamental parameters of planets coming from the activity of stars too. So the radial velocity measurements coming from the spectra, of course, this is correlated with a mass. We have this cross-correlation function. That is the major parameter to search for planets. We know from the last years that the mass of the planets coming down and down and down because the technology is better, the physics is better. That is the limit of the one Earth mass, and this is the kind of precision that we need to detect the Earth-like planets. And that is really a milestone for the radial velocity today. So instruments like Espresso, GCLF, Express, we try to determine planets in this range of mass. And of course, this planet is around solar-like stars, and these stars has a lot of activity. So the activity injected from, the noise injected from the activity is given this 1 or 2 meters by second in the case of quiet star. That is a lot when you think about the detection. And of course, that is not possible to put out only with new instrumentation. That is intrinsic, is a fundamental behavior of the star. So, talking about noise, in fact, this noise coming from several sources in different time scale. This noise could come in from granules, spots in the time scale of days, slow rotation, of course, days to week, and magnetic cycle from decades. So this is it's the sun. I mean, I put here the magnetic measurements. This is magnetograms from the sun over the time. You can see that the sun changed a lot along the cycle. That is the same behavior for all the stars like the sun. So there's the sun again, and we can see here spots. In for some case, the sun has period that rotate with a rotational period from 50 days until 50 days. So that is, it's really hard to do a big picture taking account these kind of variations. So stellar rotation is a fundamental parameter. So that is like metallicity or mass change a lot of the evolution. We know today that rotational period could come in, I mean, could be measured from spots that pass through the star, but also from spectroscopy. And know the rotation for the solar twins is an ongoing project that we have at the Natal University. So a big picture from the rotation. In fact, star started evolution with a low rotator in rotational periods. These rotational periods come up and go down. This is the zero age main sequences here, and here you have the age of the sun. In fact, in the zero age main sequence, we have a kind of, we have a scattering in the rotation that is a function of the tidal locking between the star and the disk. This period between the convergence of this line and the age of the sun is the basis of the gyrochronology ideas. So people try to use rotation to compute the age of the stars. So this is the same kind of plot, but with real data in the models. And all these are data from the ground. And this NGC 6811 is a cluster observed by Kepler. That in case, here we can see the same data. We can see how stable are the spaceborne measurements from Kepler. Of course, a problem here that we have no measurements for low mass stars. Again, this is all the satellite that we can use to determine rotational period from space. Of course, now we expect it for tests in the next month. This is a nice news for this year, and also plateau in 2024, just to give you an idea in long-term period. So Kepler gives us this nice kind of like curves for many of the stars. This is effective temperature, rotational period, and variability of these like curves. We can see, we can see here that the spot dynamics, I mean, the spot changed the position and the dynamics of the star changed the light curve. So this is a very, very nice example of a light curve. And for some clusters, we observe it also with Kepler, few stars. For example, here, we got 100 of stars in this position of the NGC 6811 with Sorry Mabon. That is one of my projects at CFA. And we got rotation. So what we can see here is that for many of stars in this cluster, the rotation is more or less the same. Of course, the dynamic of spots and all the physics changes from star to star, but this is a very, very nice result. Some stars are completely stable, some stars are not. That is normal. So we can see here the tools that you use. Here is the light curve. This is the lumps cargo analysis that we do for the stars. This is the power spectrum, autocorrelation function, and this is the phased light curve. So we can see that the rotational period here, 3, rotational period 3, rotational period 3, independent of the tool. That is a nice example of how stable is this star. But some stars are not. This is another example. Here you have a completely stable and boring star. And here you have this, oscillating rotational period. That is probably like the sun and the old stars. Just to summarize the rotation, rotation was measured from space for more or less 3,030 stars. That's a lot of stars. And that is the paper from McKillen. And of course, this is a plot of all the stars. We can see that stars, rotational period is a function of color index. This is the Kepler data. This is the M dwarf stars. This is the Malte-Wilson, the Baliuna rotation periods from the 18th. Question that is open today, we don't know, probably this is a bias, but it's why 3,000 stars from Kepler has no suns. The sun position is around here. It's more or less hard in the Kepler data. So, from the magnetic activity, a second point of my talk is the magnetic cycles. So it's well known that the sun has this cycle. This is the number of spots by year. So we can see that each 11 years you have this cycle. Sometimes the distribution of sunspots are unique like that. Sometimes are double peaks. And in the last years you have this come down. Some people talk about this small ice period like around here. And a possible theory to explain the cycles need to explain the general behavior and also this kind of behavior. So another point from the cycle is this the Malden minimum period. That is another open question if all the stars has the same behavior. So one of our students, Natal, tried to convince me first that this is a good example of a Malden minimum star, Rafael, that is here. So another feature from the sun is the butterfly diagram. So the butterfly diagram is a consequence of the spots migration. So spots coming to the equator. When we see this plot over the years, we can see this butterfly, geometry that repeats again and again over the year. So again, one model to explain these cycles need to explain this feature too. So, of course, the key element is the magnetic field. And the magnetic field has these spots, but have also this white region, these plates. And today we know from the magnetograms that these white and black regions, in fact, are part of this magnetic pole. So models that explain the large scale field of the sun need to explain at the same time this small region. That is a really, really hard problem because it involves different scale, different regions, different physics. Another result from the sun that is used from this exoplanetary hunt people, it's this connection between radial velocity and the calcium-2 measurement. So we can see that it's completely correlated. So if a star has this variation in radial velocity and, of course, variation in calcium-2, this is not a planet, but this is the magnetic feature. And from the theory again, we know that the cycle, to explain the cycle, the theory is based on a dynamo theory. This is not a linear theory, but it's a turbulent theory. And we need some dynamo because the scale time of the evolution of the magnetic field in the sun is larger than the time scale of the diffusivity. So this is the base of the Parker model and explain a lot of things. The Parker model it has this fundamental basis in transform toroidal and colloidal convection, and it is the source of the magnetic field along the time. So from this, another ingredient from the dynamo theory is the internal rotation of the sun. We can see here in the frequency, this is the profile of rotation. So in the interior, the sun rotates more or less with a single value. And here you have the split of the value. This is the surface. So this is the fundamental results from the theory of the differential rotation in the interior of the sun. So other stars also presenting similar features. And that is well known from the 18th. This is the chromospheric activity. It's completely similar to the variation of brightness that is also like the sun. We can also determine cycles from stars. And one of the tools to do that is the TSI, like in the sun. We can see here the cycle from the photometry. Here, same kind of series from calcium-2. And here, the spot number. One exercise that we did last year was try to determine the rotation of the sun. This is a little bit depressed because from the sun, we use Lambda-Chicago. We know that the rotation of the sun is around 26. Look at calcium-2. This is all the data. This is the minimum. This is the maximum. This is the TSI from Virgo. TSI from TIM is two instrument. This is the calcium-2. So this photometric data in the full, when we use the full data, never give us the good rotation of the sun. And for calcium-2, we got the good rotation only when the star in the minimum. So this is a good rotation of the sun. Another way to show the same results, look at this is the TSI, this is the minimum, and I did a Lambda-Chicago for each one of these regions. So we can see here the magnetic features, here spots and magnetic features, here nothing, because this is the minimum. And that is the Lambda-Chicago of this data. So I slide a Lambda-Chicago, and we can see that in the maximum here, in the maximum here in the cycle, we never got the synodic rotation of the sun. So the synodic rotation of the sun, it just got well in the minimum. Okay. So this is to give you an idea how hard is got a simple rotation from the sun. So this is more or less the same results, but in a different scale. So I did the same exercise, and I compare here the different values. So we can see that around 2008 and 2009, the rotation of the sun was more or less stable, and here is scattering. So the same behavior expected from stars. So, of course, we can use all the proxies to determine rotation, activity, all this. We can monitor it from calcium-2, that is what we speak today, but you can use X-rays, photometry, of course, seismology, and Zeeman Doppler imaging. That is what I talked today, and I will continue with this. And just to mention that this is not new. This is from the 18th. So that is the spectra, it's part of the spectra of the sun from the minimum and the maximum. So we can see that the calcium line, this calcium-2K line, is completely different between the maximum and the minimum from the sun. This is the same for many of the stars. That is well known because many of the surveys use this line. So a lot of stars has this data today. The emission line here, it's more or less automatically computed now from ARPs, from all the instruments. And this is completely connected with the number of spots. Here, a few examples of cycles from stars. So many of stars has this nice solar-like cycle. Some are not really nice, but are okay. And in fact, we can use all this data. It's not many stars, but we have 250 stars that can be used to put the sun. It makes sense in a panorama. I mean, in a big picture of how connected the sun and the stars. Here, for the sun, we know that we have this 11 years cycle and this 27 days for rotational period. The question is, what's happened if I put in the same diagram all the stars with cycle and rotation well known. Oops, sorry. That is the answer. The sun is here. We have no stars around the sun. That is from Baliunas' paper in the 90s. And the explanation from Baliunas was that there is two kind of a dynamo. One that operate for active stars, and other one that operate for inactive stars. That's mean, in other words, that the sun is a kind of spatial and the transition between these two lines. We got another version. We collected all the observations. We did new cycles, and we put all the stars together. So the panorama, now the picture is a little bit different. The sun is here. Many of stars appear here. So we collected all these cycles. And in fact, the question is, we have a lot of cycles different. Different from Baliunas. We have this intermediate branch of cycles connecting cycle period and rotation. So the sun is not more alone in between the cycles. So I would like to show this true star because I spent a lot of time observing these four objects. This is Capacete 1. This is a proxy of the young sun. This is 18 Scorpion. This is the best solar twin we know. And this one, of course, this is another one. This is the data that I use from the ground. Okay, you can see here for the Capacete, the quality of the cycle. This is a 21-year cycle. So we can see also the quality of the cycle. I talk about the quality because many of the stars are not good. Okay, let's talk a little bit more about 18 Sco. So 18. Oh, sorry, I forgot to these points. That means that for few of the stars, we have not only one component of the cycle, but we have two components. That is not yet explained by the theory. So here it's 18 Sco. So in fact, this is not a fit, but this is a superposition of the 18 Scorpion spectra in the sun. So I think, well, I cannot see difference between these two stars. That is what we call a solar twin. And for 18 Sco, Jeffrey Hall published a cycle in 2007. And that is a nice paper from Jeff. And he say, okay, that is a 7-year cycle. It's fine. So we keep on observing, and now have this. The problem is that if you consider this point to this, it's not 7, it's the double. If you use this, it's 3. You know? So this is a kind of example to show that finally, what's mean a cycle? The problem is that if you use all the data, that is the Lambda-Chicago again. So if you use all the blue data here, you got this value. If you have the black, all the data have this black value. This 6.5 or 30.9. It's possible cycles or cycle period for this star. So one way to interpret that was published last year in this paper, when we just say that, in fact, the magnetohydrodynamic models give us cycles that are not deterministic. For 3 different models for the same star, we can get different values for cycles. That was published for us last year, and in fact, it was nice because this news turned around the world, and this was the answer that we put, in the front of the paper. Are the sun a solar type star? Of course, we talk about in terms of magnetic stuff. So, and planets. So let's come back now. Once cycle is good, rotation is done, okay, and we need to discuss what the connection between this stuff. How much time it's I have? Okay, good. So, look at this is all the rotational period collected from the space. There's a lot of data. This is the M dwarfs. As I told you before, this is the Baliunas sample. This is the sun. And of course, these M dwarfs, it's very, very nice targets today to search planets because a lot of planets from M dwarfs are inside the habitable zone. So that many programs from radial velocity in the infrared use M-dwarfs as a perfect target. If we just change the view of the plot and you just turn in 9 degrees, you have this. So why I did that? This is rotational period and mass. In fact, this region I can just reproduce here. You know, that is the rotation that's coming here. That's the Jocker chronology behavior. The M-dwarfs, this square here, is just this square here. So in fact, if I try to get the periodicity from my data, all the periods in these regions coming mainly from rotation. That is why I put this in this sense. I can add to this plot the habitable zone. So the habitable zone, this green region here is from this Koparupu paper in 2013. It's a kind of optimistic and conservative, manner to compute habitable zone, because habitable zone is not a closed concept. People use only the distance from the star, and in fact have all the parameters that are important. So of course this is important for planets, and here I just put the sun. If you put the sun here, okay, the sun has 27 days more or less. This is 10% of 1 year, okay. So the sun is here, 27. The Earth is here. It's fine. I mean, it's 1 year. And this is the cycle. In fact, in this diagram, stars in this part of the diagram has more or less rotation period in this region, cycle are in this region, and this is not, I think this is the part of the diagram where we can put good planets and kind of good habitable zone. If you put the planets there, of course, that is only few targets complicated, like these two that I show in the 2 first slides from this talk. I would like to mention that stars with planets in this region is fine, but stars with planets in this region is really complicated to disentangle the signal of the star from the cycle. I give an example. If you observe the Earth from another galaxy, and you try to detect the Jupiter, it will be hard to separate the Jupiter orbital period, that is 11 years, from the cycle of the Sun, that is 11 years too. That is the case of all these planets in this region. And here we have the planets in the rotational period region. I would like to take some attention to this L Horloge B planet, because if you look at the rotation of the star, we don't know how's the rotation, but you need the rotation to say something about this planet. So this is one of the conflict in the literature about the planet. The second one is Alpha Cent B that Andy just mentioned yesterday, that is not more a planet, if you understand well, but it was some activity stuff. This is a Nature paper in that. Wow, from L Horloge, we try to, this is the first paper that we published this year, and in fact, we say that the rotation for the star is 5 days. That is not easy. Look, this is the S index. This is the activity index in time. So, if you understand well, I cannot see a very, very nice cycle here. But you can see that for this young star, the data show a really complicated cycle. I mean, this is an irregular cycle. So, what you can say about the planets, we need first to determine the rotational period. So, in case for the rotational period, we have determination from Steve Sawyer in 1997, comes from 80 days, 8.6, 8.5, and finally 5, and now we determine at 5 days. Here again, what kind of panel we use to determine planets and rotational period from the star. So it's really hard to say which of these peaks are from rotation or from activity. So I stress again that if we use different instruments, sometimes we got different results. That is another complicated stuff that's coming from resolution exposition time, quality, all this stuff. So for L-horloge, I would like to show another interesting thing. That is the S-index again. This is the lumps cargo from this data. And this is the original plot from Travis Metcalfe in 2010. So this is a nice, well-defined peak in 8.5. But the question is, why Travis started this plot in 5 and not 0? In fact, the answer is here. So if you do the same analysis from Travis, same data, everything equal, you have this peak here. So I have no reason to put this out. So in fact, that is one of the problems behind the definition of the planet of L-horloge. Again, come back to this is in fact is the plot from Andrew Vandenberg and Plavshan 2016. This guys put this data together, and it's really nice way to see the cycle and rotation interference and the exoplanet determination. Of course, this region is where we expected to explore these optimal G stars with planets in habitable zone. So let's summarize the things that I talked today. So in fact, the message that I would like to give you is that cycle is complicated because it's a nonlinear theory. So that means that from simple stars, we can get different cycle values for the same star. That is really complicated. Another problem is that when you talk about cycles, we talk about convective zones. And it's impossible to compare different stars. So to give an idea, today in the cycle have all the metallicity, different mass, and the people try to do a general theory with really different stars. Another point is that all the simulations is in a turbulent regime, and that is really far for the theory today. Lesson again from the cycle. So it would be a challenge to the theory to explain this half cycle and double cycle. That is not artifacts. That is probably active regions, different active regions in the star, not exactly opposite, but this is a real result from the data. The small planet detection are, of course, function. I mean, the detection of small planet is function of this activity. So we need to know really well, the activity behavior of the stars to be sure that the planet's there. Of course, models are good, Bayesian models, Gaussian process. All this is very, very nice stuff, and it will help in the next years. Sometimes that is true for many of cases. The one particular indicator correlates with radial velocity, but the other now not. So this is another problem because some exoplanet hunted use only one indicator of activity. A combination of optical and infrared radial velocity probably will be a good way to do things in the next years. By 2009, I expected I'll be like that, a little bit older, but still alive. What we can do? So first of all, combine different telescopes, different wavelengths, different techniques. This probably will be very, very positive. By 2013, Kepler will observe a lot of stars, but TESS, Plato, we give us a nice 21 points, 21 coverture of data. That's probably will be very, very nice for compose good targets for search small planets with GCLEF and other instruments. That is, I call this the golden stars. Probably now pick up some quite well-known star is the good way to search for small planets. Of course, understand the physical process that is part of the continuum process in astrophysics. That's important too. And strategically sampling the data. So if you know the magnetic field, we can search of course, for periods out of the rotation and cycles. So I would like to spotlight here and take your attention to this Boston co-star this summer. And these two sprint sessions. One from light curve rotation and gyrochronology. That is one of the focus of this meeting will be discuss the gyrochronology in the context of this rotational period. And the second one is this one from the stellar brightness variation, building on the solar chronology. This is also a nice splinter session that's come back to the sun discussion in how use the sun as a lab for exoplanet search. So that is all. Thank you.
So can I start with the questions? So, José, yes. So you mentioned towards the end of the talk about the use of model comparison, so a way to sort if there's a rotation issue or planets. So just to be clear for me, so how many parameters does this problem have? So how many numbers you need to model the stellar rotation or the effect of the planet, so far as to have an idea of the magnitude of the problem in a statistical way?
Okay. Yeah, well, actually, people use, I talk specifically about one model that's called SOAP. That's from Xavier Dumus from CFA. And in Xavier model use time life from spots, rotation of the star, cycle, mass, metallist. I think mass metallist is not yet there because it's just simulate the sun, but 3 parameters. And in this, give this light curve, the guys inject the planet and try to recover. It's not good yet. It's not good. Probably you have all the parameters that is we need to put, but we can search for the soup. This is the code that Xavier used, and in fact, rotation period, activity. Activity means the cycle.
When you introduce a planet, how many more parameters you put in the problem?
Well, the injection of the planet, you have this series. The data is there. You input one planet with a specific parameter, and we try to get the planet to recover the period. And in fact, the only parameter is the orbit of the planet.
Is the rotation period,
yeah,
or
we have the rotation,
eccentricity, or
the
no?
rotation of the star and the orbital period of the planet.
Mm-hmm.
Both are inside the data. So yeah, disentangle it's a problem. Yeah.
Okay, thank you.
José, I heard from you in another occasion that including molecules, you can have some molecules in the star spots that can mimic the molecules in the atmosphere of the planet. Is this right, or I understood wrongly?
A good question. 2 weeks ago, it's because of Mercedes Morales at CFA, and she's has this nice project to transit spectroscopy, and people try to detect the atmosphere of planet when the planet passes in front of the star, and the molecules from atmosphere comes in this sense. But observing the sun now with the very high resolution, we can see a different chemical signature from the region just around the spots and the region a little bit far away from the spots. So imagine if you try to detect a planet that's passed just close to the spots, it's impossible to see if the molecules or some signature, chemical signatures, come from the star itself or from the planet. So this is another question about how far we can go in this way without know the sun first. Yeah.
So I guess what I took away from your talk is that it's difficult to disentangle between stellar rotation, activity, and say a possible single planet. But of course, many of the Kepler systems show evidence for multiple planets. And so I'm wondering about, does this help the case for if you have a signal that shows evidence for multiple planets? Does that help this ambiguity, or does it make it worse?
Yeah, sure. I mean, the number of planets, it's many planets. Of course, it's hard to see because you have all the components in the data. But yeah, well.
But if let's say you see evidence for 5 or 7 planets, then if you want to explain this with rotation,
I don't understand the connection between many planets and rotation. I mean, many planets don't figure out a different rotation. So for today, you have no disconnection about the rotation, the quantity of planets. All the statistics of star with planets and without, or multiple planets, the star has the same rotation. That is probably because only really close big Jupiter can affect, in fact, the rotation, or the rotation is a function of the history. So you need to integrate all the history of the star to understand the actual rotation that we observe. So that is not, last years or last mega years fact.
I'll try to rephrase my question in the break.
Okay, thank you.
So, more questions? So I have another question. So is there a particular wavelength that makes your work easier?
Yeah. In UV, we try to, from the sun, of course, we have no for those stars, but when we try to track the same light curve that I show from the sun, from the UV, the rotation is a lot more stable. That is because the contrast is different and the plates, it's more visible in the UV. So probably the LUVA, this satellite, this planet from NASA, it would be nice to see this rotation. But UV, it's good. From planets, the infrared is good too, because the contrast is also easier. I mean, in the infrared.
I have a question. So it's more difficult for you to disentangle, the activity of the stars and the rotation and the planets around it, and the effect of the planets around in photometry as Kepler, or radio velocities as other instruments?
Well, there's two problems. I mean, in photometry, the transit is really clear. I mean, you have this transit there. If it's not a binary,
periodic.
Yeah.
Very periodic.
Okay. If it's not a binary, I mean, the secondary transit is not there because of the planet. But the planet's confirmed by spectroscopy. So we need spectroscopy to say about the mass of the planet and all these parameters. And this confirmation from spectroscopy is the problem.
But for example, with Kepler, for example, if you have a spot in a star, it's also will be periodic, right? Like a planet in an eclipse.
Could be a binary, or depends on the secondary transit. But yeah, this is periodic. And after this is a candidate, and the clap is the KOI. And the follow-up is from the radial velocity. So the planet is confirmed, the mass is computed. This is the second stage of the exoplanetary search.
Someone else? So if not, let's go outside and take our group photo and then have the coffee break, all right?
Excellent.
Thank you again.
Thank you.